Thanks.
No problem. Yeah.
He stole my pencil, which is why it took so long to get to that question. He stole my pencil. I was looking for it.
I
Instead
did,
of pressing the button.
steal his pencil.
Legitimately stole it, straight up.
When we took
Yeah,
this,
just
you want us to
thieved
put
it.
in the page.
Burgled.
Okay, so. Okay, any questions on the assignment? Any ones you want me to go over? Yes? Number what? 20? Yeah. Okay, so if you look on 20, right? So here's the deal. There's a couple, and again, I beg of you, when you start these problems, the dumbest thing that you can do is go right to an equation. It's just going to be a train wreck, okay? So if you look at what's happening on 20, it can go from 0 to 80.5 kilometers per hour in 8.2 seconds. So your velocity time graph is going to start at 0. Here's 8.20 seconds. Boom. You have your final velocity. Now, how many significant digits did I give you in every value? 3. Guess how many I want in your answer? 3. So, the first thing you got to do is to say, okay, hey, how long is it going to take to speed up from 48.3 to 64.4 if the acceleration is the same as when it's going from rest to 80.5? So basically, I'm telling you, you're going from 0 to this velocity in a certain amount of time. You can find that acceleration. So how does that acceleration play into this graph?
It's the area.
That's your slope, right? This is going to be the slope of the line. So what I'm telling you is that you're going to use this same acceleration, you're going to use this same slope to basically figure out how long it's going to take to go between these 2 points. So you've got your time. I've given you the two velocities. You want to figure out how long it's going to take. So basically, you're going to go to a y-intercept. At this point, you're going to know the initial velocity, the final velocity, and the acceleration. Find the time. Now, when you convert those kilometers per hour into meters per second, make sure that you keep at least 3 significant digits when you convert kilometers per hour into meters per second. Do not round it, okay? Then your whole answer is going to be screwed up. Round when you get to the end. Now, let's talk about number 17, even though nobody's asked about it. So at 17, you're going from 20 kilometers per hour to 0 in 3 meters. What is missing in all of 17? Time. So what are you going to use? That equation, okay? You don't have time. Don't sweat it. This is the beauty of that equation. But, again, look at it this way. Look at the big picture. This velocity time graph is going to go from 20 kilometers per hour to 0. And you're told that that area is 3 meters. Change that into meters per second. Okay? It's like 5.56, something like this. Now, then we're going to say, okay, hey, now we're going to stop the car, but we're going twice as fast. So this area is 3 meters. So, and the key to this is that it's going to have the exact same acceleration. So now we're going to be up here around 11-ish meters per second. And we're going to start with, and we're going to use the same acceleration. So what is the significance of the same acceleration in terms of this velocity time graph?
Same slope.
It's the same slope. The line's going to be parallel because you're using the same acceleration. So here's what you're tempted to do. You're tempted to go, well, if 20 kilometers gets me 3 meters, then twice as fast, going 40, should just take me 6 meters, and boom, I'm done. Okay? You're tempted to do that because, oh, it's a simple linear relationship. Double the velocity, double the stopping distance. But here's where this fails. If you look at this equation that v squared equals v naught squared plus 2ax, as soon as you see that these things are squared, it cannot be a simple linear relationship. Just like when you look at distance equals 1/2 at squared, as soon as you see t squared, it is not a linear relationship, it is a quadratic relationship. So, in no way, shape, or form can you go, oh, I'm just going twice as fast, it's going to double the distance. It's not. So if all goes well on 17, your distance should be between 10 and 15 meters on 17. Okay? Now, on number 11, with the gal sliding into second base, I just want to point out some potential pitfalls that I've seen. So if you look at what's happening on number 11, here's second base. She's sliding in, right? Got an initial velocity vector of 4 meters per second. Velocity time graph is going to look like this. Pay attention to everything that I want labeled on that velocity time graph. I want the initial velocity, the final velocity, and the slope labeled on this graph. You can do it on this sheet of paper. You don't have to put it on graph paper. But just draw it big enough where I can clearly see everything that is labeled. Okay? Now, one of the things that you want to figure out is how fast she's going at 0.3 seconds. Okay? So you're trying to figure out this velocity at 0.3 seconds. Now, is it physically possible for her velocity to be a negative number at 0.3 seconds? Ethan, why not? What would that mean?
That she's speeding up.
Not that she's speeding up.
You just can't have like a negative velocity.
Well, what would it
She
be?
changed direction.
Yes. So you're saying that she's sliding in this way, going with a positive velocity, but at 0.3 seconds she has a negative velocity, which means she's going in the opposite direction, but then miraculously at 0.5 seconds she's at second base. Not going to happen. You also know that at 0.3 seconds your velocity, number one, has to be positive. Because if you just go to 0.3 seconds and go up here and go, oh, I have a positive velocity. But it also has to be less than what? What does your velocity have to be less than at 0.3 seconds?
4 meters per second.
Yeah, it's got to be less than 4 meters per second. She can't be going faster than 4 meters per second if she's sliding to a stop. So you know two things about this answer at 0.3. It's got to be a positive number and it has to be less than 4. So if your answer doesn't meet either of those criteria, something has gone horribly wrong. Now, I emphasize this again. You have to view your paper through my perspective. I've got 51 of these to grade this weekend. When I give you sections like on this one, A, B, C, and D, on your answers, I want to see, here's the answer to A, here's the section B, here's section C, here's section D. Make this easy for me to grade. Love y'all to death. I'm not going to spend my whole Sunday afternoon sorting through random numbers that that make no sense and have no units and there are no equations. Okay? Very bad things are going to happen. Love y'all to death. I'm not going to waste my time. Okay? So, great.
I had a question on the graph for number 10.
Okay.
I'm wondering if it was quadratic or just linear.
No, it's just a linear. All you have to do on number 10 is here's the velocity time graph. Here's your 2 points, label them, that's all you have to do.
Oh,
The only thing you know are those 2 points.
right.
It's just an x and y coordinate system of time and velocity. That's all you have to do. And it has to be linear, otherwise you can't find the slope.
Right.
Talk to me.
I got on 11
Yeah?
for D, 11D, I got a negative number.
On 11D,
Yeah,
where you're trying to find the,
how fast she was moving
Accelerate.
at 0.30, so
okay, look. Stop. What do you have as the slope of this line? On number 11, what's the slope of your line? Which is your acceleration.
which is my accelerator, I don't.
Let's find your acceleration.
Okay.
Our initial velocity is 4, our final velocity is 0, right? So I'm going to go 0 minus 4 meters per second, divided by a half a second, because I know acceleration is v minus v naught over time. True?
Yeah.
So this is going to be, trust me, negative 8.00 meters per second squared. That's the slope of the line. True?
Yeah, I think I did that just with 0.3.
Yeah. No, because the slope is, you got to use the entire 0.5 seconds to find the slope of the line.
Okay.
Then, You're gonna go V equals V naught plus AT. Here's this y-intercept. That's still 4 meters per second. Your acceleration is still negative 8 meters per second squared. Plug in 0.3 seconds. All of this is a y-intercept. People, don't lose track of the force for the trees. This is just nothing but a slope-intercept equation. That's all it is. Okay? We call it physics, but this is just basically a linear equation with the slope-intercept that we're calling time and velocity as opposed to x and y. Okay? That's all it is. Don't lose the forest for the trees. Okay? Anything else? Going once. Going twice. So here's what I want. Just so you have it all together, staple that blue sheet to the front. Also, and this is particularly true, guys tend to screw this up more than girls. It's not sexist, it's just a true statement. Because I'm guessing you might have multiple pages. Look at your pages and make sure that they're in sequence, okay? So that when I'm grading it, I don't open up to page 1 and see number 12 at the top of the page, okay? So make sure that when you staple them, that it's all in the correct sequence, okay? Now we're good. So,
Because I'm sad. That's why I'm sad.
Also, save this into the camera.
I guess you could go like gravity. Gravity makes me sad because it's constantly keeping me down.
You hear that, guys? Gravity's keeping Eric sad because it's constantly keeping him down. Eric, please stop talking to me. Hear that, guys? Matt got pissed at Eric. I'm still mad. Not my water bottle. You jerk. It's just a minute of us saying stupid gravity stuff in bird band on the board. Do you think they have gravity in Australia? No, that's why they got this crazy hardness.
They fall off.
They have gravity. Well,
when a child is born.
well, they have gravity. They this for science.
Yeah.
They just gotta harness everyone and see if they throw.
Gravity is what happens when you fall off the edge of the earth.
huh?
It's going. I've got like a minute and a half of you writing stuff on the board.
And a couple of our bad puns.
Yeah.
You can enjoy watching those.
Oh, yes.
15 word problem?
Yeah, 15 is a matter of fact. Wow. Okay, so here's the beauty of gravity. Number one, we wouldn't be here without it. The universe would not exist as we know it because you would never have stars forming and there would just be random particles moving all the way around. Big question is, why does the universe have gravity? We don't know. We're just happy it does. So, the beauty of gravity calculations is that there's no new equations to learn. It's the exact same 4 equations that we learned up to this point. It isn't like, oh, gravity behaves differently than if you hit the brakes on your car. It's the exact same equations. There is no new equations to learn. The only difference is that instead of using a generic A for acceleration, we let that acceleration be a very specific value of negative 9.80 meters per second squared. Now, usually we just write it as negative 9.8. So technically there are 3 significant digits in that gravitational acceleration. So don't look at this, oh, g is negative 9.8. That only has 2 significant digits. Technically it's negative 9.80. Okay, so technically there are 3 significant digits in that number. G, no matter if you drop it or if you throw the ball up in the air, doesn't make any difference. G is always going to be negative 9.80 meters per second squared. Always. Do not think, do not go, oh, make that positive. No, in any acceleration problem, G is going to be negative 9.8 meters per second squared without fail. Now, amongst the long list of things that irritate me, do not say, oh, gravity is negative 9.8. Okay, the love of God, that is so wrong, okay? Gravity causes an acceleration of negative 9.80 meters per second squared. Okay, that's legitimately true. But the only reason we have that acceleration is because of gravity. So don't say, oh, gravity is negative 9.8. No, it's not. It's not. It's not. It's not. You missed the whole point of gravity. That's just the acceleration caused by gravity. Okay, now here's going to be the fundamental difference. So here's Gary the golf ball. So if I just hold Gary the golf ball up and I drop him, V naught's going to be 0. Okay, it's going to make life simpler because if you look at a lot of these equations, that involves V naught. So if V naught drops out, that's going to be a cool thing. Now, if I throw Gary, I can throw Gary one of two directions. If I throw Gary up in the air, then my initial velocity is going to be a positive number. If I take Gary up in the air and go, you know, Gary, I really don't like you. Not only am I going to hold you up and drop you, I'm going to throw you down as well. So if I throw him down, then V naught's going to start off as being a negative velocity because everything going down is going to be negative. Typically, this is what's going to happen 99% of the time. You're going to have a positive V naught. Sometimes you get this, but most of the time it's not. Most of the time you're going to throw something up in the air and see what happens. The displacement. Typically, when you're going to drop something, you're going to make that point of release be the reference point. We're going to make that 0. Then going down, and this is what this is referring to, then your positions going down are going to be negative numbers. And you'll see why that's important later on in terms of making things work underneath the radical. On the way up, if you're going to throw it, typically the ground is the reference point. So I would go, or at least the point of release is the reference point. So if I go from here to here, typically I just make this the reference point and then I judge all the positions from here. Where it gets a little bit weird is like if you're standing on top of a bridge and you throw something up and then it falls all the way down to the ground. So you're still going to make the ground the reference point, but you're going to start up above the reference point and it's going to go like that. In terms of your final velocity, when this thing lands, it's going to have a negative velocity because it's going to be going down. This is going to be important in terms of how big problems work in terms of being consistent. Typically, and with this one, especially if you throw something up at the top, if you throw it up, when it hits that peak, that velocity is going to be 0. That will become your friend in some very complex problems. So if you throw something up in the air, when it reaches that highest point, you have a velocity of 0. That's going to make a lot of complex problems seem really, really, really simple. Okay, so we're cool with this. So this will all make sense once we begin to kind of work some problems. All right, so here's the setup. So let's say that I'm going to hold Gary up here, and I tell you that Gary is going to be dropped from a height of 2 meters. Okay? I'm going to drop it like this. Boom, let him fall. And so from that, I want to find the time down, the velocity at impact, the velocity at, I don't know, 0.40 seconds, and that's it. So, here's the story. I'm going to hold him up, I'm going to drop him. It's going to fall 2 meters, just going to drop it. From that, I want to find the time down, the velocity of impact, and how fast he's going after 0.4 of a second. So, even though I've given you only one number, what else do you know?
Your initial velocity.
I know my initial velocity is going to be
0.
0.0 meters per second. And what else do you know?
Acceleration,
My acceleration is going to be
negative 9.8 meters per second squared.
meters per second squared. Now, one of the decisions that you all need to make is, and here's how this will always play out. I'll always work some sample problems up on the board, and then I'm going to turn you loose and go here. See if you have to figure it out on this. Whether or not you write these down is completely up to you. Y'all are big people. I don't care if you do or not, okay? But here's gonna be the attitude that I'm gonna take. If you come up and you say, you know, Mr. Workamp, I really don't understand how to work these problems. I'm gonna say, well, did you write down the problem that I wrote up on the board? And if you say no, and that was a decision that you made, and if you say, I really don't know, I didn't write it down, then I'm gonna say, tough, okay? Because I worked the problem and you chose not to write it down, then my attitude is gonna be, I'm not gonna work this problem again because you didn't write it down. Now, you all are big people. Some people actually learn better by not writing stuff down, and they just listen. And if you learn that way, that's fine, okay? That's the roll of the dice. So I am not going to look at your notebook and go, oh, you know, did Shively copy the problem down? I'm not going to. But realistically, if you come in and you go, man, I don't know how to work these problems, and I'm going to say, I worked the problem on the board. Did you write it down? No. Well, tough. Okay? Those are just the rules. Okay. Now, you don't have to write down everything, but if you can just kind of say, okay, hey, this is the equations that we used, that will get you a long way. All right, so let's start with the time down. So we know the initial velocity is 0. We know g is going to be negative 9.8 meters per second squared. I'm going to drop this. Okay, no worries. Now, here's another option if you want to do this. Personally, depending upon your learning style, this is what you could do. This video is going to end up on YouTube by tonight. So what you could do is sit here and go, you know, I'm just going to listen. I'm not going to write down anything. I'm just going to listen. Then tonight, I'm going to go back there and I'm going to watch that, and then I'll write down the stuff. Okay? So that way I'm kind of listening to what's going on, and then I'll go back later, and then I'll write down the information that's on the board. Okay? That's another option, because you know, like I said, all these videos show up on YouTube. So that's another possibility. If you want to put in that time and go back and go, okay, hey, I'll just fast forward and I'll freeze frame it, then I'll write down the information that's on the problem that we worked for. Just another option. Okay. So we need to tackle the time down. So let's look at the equations that we've got. We got v equals v naught plus at. We got distance equals 1/2 v plus v naught times time. We got distance equals 1/2 at squared plus v naught time. And we got v squared equals v naught squared plus 2at. What about this one? Find the time.
We don't have final velocity.
Yeah, we have two unknowns. We don't know the time, nor do we know the final velocity. Probably not so much this one. What about this one?
Don't know the final velocity.
We know the distance, don't know the time, don't know that. Probably not this one. What about this one?
No.
Doesn't even involve time. That one's out. What about this one?
Yeah.
Ah, this is in our wheelhouse. Because look, what's my initial velocity?
0.
Oh, so what happens to this whole thing?
It's crossed out.
Oh, that goes away. That's kind of cool, right? So, I need this solved for time. So great. Let's throw a little algebraic prowess my way and solve that thing for time.
Alright, so you would have multiply the 2 on both sides, so it'd be 2d.
I like that.
And then you would have to divide by a,
I like that.
take the square root of all of that. That
And
would
you're going to get time. Nice. Okay. Now, this isn't a big dog equation, but it's like a pup. You're going to use this equation a lot for things that are dropped or when you start from rest and they speed up. So this isn't a big dog, but it's a very, very cool equation to use. Now, what I'm going to do next is wrong. Okay? Do not do what I'm going to do. So you're going to sit here and go, okay, I got 2 times 2 meters, and then I'm going to divide that by negative 9.8 meters per second squared. So at this point, why is this a train wreck?
You can't take the square root of a negative number.
You can, but what do you get?
Imaginary.
You get imaginary time, okay? We're not at Disney World, folks, okay? Imaginary time ain't gonna happen. So at this point, you have a solution. There's 2 possible solutions. One is that you go, okay, problem solved. I'll just make G positive.
oh,
No, I'm saying it's not a good solution. I'm just saying it's an option. Now, here's why you cannot do this. Okay? This is why that's a train wreck. Guys, look. You have to work these problems as one big idea. What's the velocity time graph going to look like? Olivia, where's my velocity time graph going to start?
At 0.
At 0. And it can do one of two things. It can either slope up or it can slope down. What's it going to do?
Slow up. Down. Slow down. So
Going to slope down. And what's the value of that slope, Olivia? Let me give you a hint. It rhymes with negative 9.8 meters per second squared. Beautiful. Good girl. Okay? Now, meters per second squared. Why is that the slope? That's the acceleration due to gravity. Okay? This falls under the Jedi-Stoffelwall thing. Stop the force and watch. If I stop applying the force to the ball and watch what happens, it begins to accelerate, which means there must be a force acting in that direction, which is what we call gravity. So that's the acceleration caused by gravity. That's going to be the slope of that line. Now, this is where everything has to fit together. Here's the slope, negative 9.8 meters per second squared. Here's what you have to understand about this. If I let this thing fall for exactly 1 second, okay, if I let it fall for exactly 1 second, how fast is it going to be going at the end of 1 second? Negative 9.8 meters per second, right? That's what that slope means. It means for every second that goes by, my velocity goes down negative 9.8. You can kind of think of it like you're at the mall and you're shopping. And the rule is at the mall, this is the gravity mall. The rule of the gravity mall is that for every second that you're in the store, you have to spend $9.80. So if you walk in the store and you have no money, at the end of 1 second, how far in debt are you?
$9.80.
$9.80. Okay? If you're there for another second, you're going to be in debt $19.60, right? Okay? So that's what this means. If you're at the gravity store, every second that goes by, this is how much your velocity is going to change, because that's the slope of the line. So if I'm at exactly 1 second, this is what this number means. That means that would have a value of negative 9.8 meters per second. Cool with this. Now, if you were to find this area, okay, I don't want the numeric value because I don't have enough information. Actually, I do. But here's the sign of this. What would the sign of that area be? Positive or negative? It would be a negative value, right? Because I'm going to multiply a negative velocity by a positive time, I'm going to have a negative area. So here's the deal. So I know this area has to be some number of negative meters. Okay? It has to be a negative value. So then you go, well, Mr. Burkham, how do you generate a negative value when it falls 2 meters? Okay, legitimate question. So here's the deal. We said we're going to make the point of release, when I let go of Gary, that's going to be 0 meters. So here's the deal. We're going to define everything going down as being a negative value. So when he lands, he's going to land with a position of negative 2 meters. Okay? He's going to land at a position of negative 2 meters. Now, how do you calculate displacement knowing position final and position initial? What minus what? Final minus initial. What's his final position? Negative 2 meters. What's his initial position?
0.
What's his displacement? Negative 2 meters. Okay? So that's consistent as long as you're defining down as being a negative value. Now, some people like to do this. They go, well, Mr. Burkham, I want the ground to be the reference point. Fine, knock yourself out. Let the ground be the reference point. Then this position up here would be 2 meters if you want to go this route. Well, here's the deal. If you make this 0 and make that positive 2, what's its final position? 0. If I take 0 minus 2, I still get. So no matter how you set this up, your displacement is still going to be negative 2 meters. Okay? Cool with this. So this is why I said you have to work this as a big idea. So that means this area is going to be negative 2 meters because I'm going to have a negative velocity multiplied by a positive time. I'm going to get a negative value here. Mathematically, it's going to work. No matter how I set this up, I'm still going to have a displacement of negative 2 meters. Now, with that said, we said the velocity time graph is going to have a slope of negative 9.8 meters per second squared. Here's 0 meters. What's my position time graph going to look like? I'll give you 3 options. Curve A, curve B, curve C. Top lip, middle lip, lower lip.
Top lip,
Why top lip?
because it starts out slow, but then it starts to increase as it goes over time.
That's right. So as this thing falls, it starts off slow, and then it's going to travel faster and faster and faster, as indicated by that slope going further and further and further. Now, here's an interesting thing. If I drew this graph and came out here to 1 second and drew the tangent line, what would the slope of the tangent line be on that position time graph at exactly 1 second?
9.8.
9.8. Why?
Because
Because that's how, no, well, it's because it's the acceleration, but because it fell for exactly
1 second.
1 second, and that's how fast it's going at the end of 1 second. Okay? So, up to this point at that, that's going to be the slope of your tangent line, negative 9.8 meters per second, if it fell for exactly 1 second. If it fell less than a second, guess what? Your velocity is going to be less than negative 9.8. If it falls for more than a second, it's going to be greater than negative 9.8. Cool with this. Okay. Now, let's go way, way back to here. So, this is a train wreck. Okay? This is a train wreck. Because I'm going to have a negative number underneath that radical. But, if you look at this in terms of a velocity time graph and a position time graph, what's the sign of that 2 meters? Negative. Miracle of miracles, now I have 2 negative numbers underneath the radical. Guess what?
It's positive.
Here's a positive value. Okay? So, but this is what you have to watch for. Don't get lazy. Don't shortcut this process. If you're getting negative numbers underneath the radical, you have done something wrong. So, somebody crunch the numbers. Take 4 divided by 9.8. And here's what you're going to do. Mark my words. You're going to forget to take the square root of this whole thing. So what do you get? So 0 point something. 0.6 what?
38.
0.638? Everybody cool with that?
No, 639.
9?
Yeah.
No, it should be 0.64.
No, because you're rounding to 3 significant digits, not 2 decimal places.
It's 0.638.
No,
You gotta round it.
You have
You
to
gotta
round
round
it
it
to
to
3
zero.
significant digits.
have to round it.
Yeah, and it is 39 because it's 388.
Oh, I thought my 8 was a 0. Okay. Then yeah, it's 0.639.
Okay, everybody cool with that?
Yes.
Seconds. Do the units work out? Because meters cancel out, what are you left with? Second squared, square root of second squared. Seconds, voila, we're off to the races. Okay, so we got that. So if you go back, time down, 0.639 seconds. So if you kind of want to do an independent verification, you let go of it. 1 missa, okay? I got the 1 missa as opposed to 1 Mississippi, which is about 1 missa is equivalent to 0.639 seconds.
Timer on it. Get our timers, we'll get it going.
No, it's when I did it, 1 Mississippi is exactly 0.639 seconds. Okay. Now, velocity of impact. Do not tell me, oh, it's 0, because it hit the floor. No. This is how fast it's going at that very split second that it comes in contact with the floor. So, because otherwise I would never ask you this question because every answer would be 0 because it hit the floor. No. It's how fast it's going at that exact instant of impact. Now, there's a couple of ways that you can do this problem. So let's go back to our smorgasbord of equations. So, could I use this equation?
Yeah. The only problem with that is that you're using time, which you found, which
Yes.
fit.
So, do I know my initial velocity?
Yeah.
Do I know my acceleration?
Yeah.
Yes.
Do I know what time?
Yeah.
Yeah.
But, like Honus said, if my time is wrong, guess what?
Everything else.
This is going to be wrong. But let's assume that our time is right for now. Is my final velocity going to be bigger or smaller than negative 9.8 meters per second?
Small.
But little. Bigger or smaller than negative 9.8 meters per second? Why?
Oh, no, it's less, because it's under a second.
It's under a second. Because you'd have to fall for an entire second to get to negative 9.8. We're falling less than a second, so my velocity has to be less than negative 9.8. Okay? So, and also, what sign does my velocity have to have? Negative value, because it's going down. This is how we define the system. So, I could do this to get my final velocity. Could I use this equation to get my final velocity?
You have to set it up properly.
You know the time,
Yeah.
right? You know your initial velocity,
Yeah.
right? You know how far it falls,
Yeah.
but this algebraically is going to be real ugly. Because you got to multiply by 2, divide by t, and then get v by itself. Okay? You could do it this way, god-awful amount of work. Okay? Now, what about this one? No, why?
It doesn't have final velocity.
It doesn't even have final velocity in it, okay? You are going down a rabbit hole of pain if you do this, okay? Because you can't get anywhere. Could I use that equation?
Yes.
Which one do you think would be best?
That one.
Why?
Because of your time.
So it's under now.
Because you're not dependent upon the time that you have found. And if you screwed up the time, then you screwed up all of these. So you always, if possible, want to work off of known values as long as you possibly can. So, my initial velocity is going to be
0.
0. So I'm going to have v equals the square root of, now I'm going to do this wrong. Do not do what I'm about to do. Oh, 2 times negative 9.8 meters per second squared times 2 meters. Why is that going to be bad?
You're going to have a negative under the radical.
I got imaginary velocities. Okay, that's a real fun one to use if you ever get pulled over by the cop. You know how fast you're going? No, it's imaginary. Welcome to my world. That point, you're taking a drug test. Okay. So, but again, what can we do?
-2.
Make that a negative. Now it's consistent. And I know y'all are teenagers and go, Burkham, why are you ranting and raving? Just pretend that it's not there. Okay? Just literally, what's the big deal? It is a big deal because you have to view these problems in their entirety. Again, this is not about getting an answer. It's about a process. And the sooner you embrace the process, then you're really going to understand how physics works. Now, this is where your calculator lies to you. If you punch these in, what does your calculator say the answer is? What does your calculator say is your answer is? Look at your screen. What does it say? I guarantee you it's going to say nothing but a positive value. What does it say? Here's what, also you're going to forget to take the square root of this.
Yeah.
What'd you get? 6.26. This is what your calculator says the answer is. 6.26 meters per second. Why is that wrong?
Because
It should be negative. Well,
Yeah.
what's the square root of 4?
plus or minus 2.
Plus or minus 2. So the square root of anything, you have 2 possible roots. So guess what? You just choose the negative root. Okay? That's all you have to do. It's easy. Yeah, just choose the negative root. Okay? It isn't a big deal. But your calculator probably won't give you this option. Okay? But this is why you look at it in the context of the problem. So it's negative because of the fact that at this point, we were at like 0.6 something seconds, and we're here at a negative value. That way it's consistent. Now, so there's pros and cons to this. The advantage of using this equation is that you're going off of known values. The disadvantage of this equation is that at the end you have to choose the negative root. Okay? That's the disadvantage. But it's balanced out by using known values. If you went with this equation, okay, so let's say you go, wow, Mr. Burkamp, I like slope-intercept. Okay, good, I'm happy. So you got v equals v naught plus 8. So you've got 0 meters per second plus negative 9.80 meters per second squared. And what was the time? 0.639 seconds?
Yes.
Okay, so here's the advantage of this. So I'm going to take negative 9.8 times 0.639. Oddly enough, you get the exact same velocity. The advantage of this equation is that it automatically gives you the negative sign, and you don't have to think about it. The disadvantage is that if the time is wrong, this is wrong. So it's just whether or not you're willing to roll the dice. Okay? So if you're solid on the time, you can do this. But if your time is wrong, this turns into a train wreck. Okay? Cool with that. All right. Now, and this matches with what McGriddle said. Because it's fallen less than a second, my velocity is less than negative 9.8. Cool with that. Now, the last thing we want to do is we want to figure out the velocity after it's fallen 0.40 seconds. There is only one way to do this one. There is no alternative. The only way that you can do this one, because you're given the time, the only way that you can do this is use v equals v naught plus at. That's it. There is nothing else. This is the only way that you can do this. But you know your time is 0.4, your acceleration is negative 9.8. Just plug in the numbers. That is the only way that you can work this problem. There is nothing else because you don't know anything else. So, but again, bless you. So, it's not painful. So again, if it fell for 0.639 seconds, that velocity of the impact was negative, what, 6.26? So does this velocity at 0.4 seconds, is it going to be bigger or smaller than 6.26?
Smaller.
Smaller because it hasn't fallen as far. Okay? That's it. There you go. Okay? Cool with that. Okay. Stop that. Stand up. Take a stretch. Move the ball where we throw it. So now we're going to change it. And we're going to throw a ball up in the air at 20 meters per second. So we're going to take Hank and we're throw him up in the air like this. And we have a note that says,
Nice hands, feet.
yeah, like and subscribe. Okay,
Like and subscribe,
yeah,
turn on the notifications.
okay.
Hit the bell.
And then try and find me a sponsor.
Slap
Okay,
that bell so you never miss out on
So-
Bert's voice.
this is the only number that you know. What?
Nothing. You'll hear it later.
Yeah.
No, that implies that I go back and watch them. And
Are you
it's like, I
serious?
know what I said.
You
I
should
know what I
probably
said.
watch.
It's weird watching yourself teach, you know?
Really?
You should probably watch because of what we say.
Wow, the technique right there was kind of weird and probably blocked someone's view. You don't do that?
You can do like
My view right now.
I'm there with the teleprompter screen.
You grade yourself?
Yeah. No. Oh, that was probably solid on that one. All right. Good follow through. Okay. All right, so I got a initial velocity of 20 meters per second. That's the only number that I know. So from that, I want to find the time up, the time down, and from that, the total time. And then I want to know the maximum height. Okay. And then I also want to know the velocity and height at 1 second, and then I want to know the velocity and height at 3 seconds. So I want to find all of this only knowing one number. So I got one number. Now, here's the deal. What else do you know that I did not explicitly write down?
Acceleration.
Acceleration. What's the value of the acceleration going to be?
Negative 9.80.
Negative 9.80 meters per second squared. Right? So now think about this. There's a couple of different ways you can represent this motion. As soon as it leaves my hand, what's going to happen to that velocity vector? It's going to do one of three things. Get bigger, get smaller, or stay the same.
Get smaller.
It's going to get smaller. So if this is my initial velocity vector, then V2 is going to be a little bit smaller. V3 is going to be even smaller than that. So, Vonda, is it accelerating on the way up?
Yes,
Yes. You hesitated like it might not be.
it is doing that.
So, Vonda, since it is accelerating, right, we've established that. What's the direction of my acceleration vector? Is my acceleration vector pointing up, or is it pointing down? Up.
Yes.
Yes. So, you're telling me that my acceleration vector is pointing in the same direction as my velocity vectors?
No.
No. No. Because if my acceleration, Vonda, which would be cool, don't get me wrong, okay? If this happened, I could still dunk a basketball if this was true, okay? And I'm old. So, if this was actually true, if my acceleration vector pointed in the same direction as my velocity vectors, when I let go of the ball, what would it do?
Get faster.
It would get faster.
That'd be like living in Australia.
Is that what happens?
No.
No. Okay? We would ban trampolines. Okay? Because if that's what happened, little Timmy would bounce on the trampoline and go get faster. Like what happened to Timmy? I don't know. He's
Got
gone.
his ground.
He learned his lesson.
He learned his lesson.
I can teach you, literally, I can teach you all of gas laws and thermodynamics using second graders for Timmys. There's an honest God
A
truth
second
statement.
grader.
No, it's true. Yeah. And if he goes to the zoo, watch out by the lion cage. I can explain valence electrons using Timmy at the zoo too. Okay. So, but Timmy does jump off the
We're talking about kids
trampoline,
being
right?
killed by lions.
But what actually happens to Timmy? Unfortunately, Timmy comes back down.
Oh.
Unfortunately. If you knew Timmy, that would be an honest guy.
Ghost crucible.
So, Vonda, which direction does my acceleration vector point?
Down.
Atta girl. Okay? So, it points in the opposite direction because of the fact that my acceleration vectors are going to be slowing me down, right? So I'm going to have negative acceleration. Olivia, what's the value of that acceleration?
Negative 9.8 meters per second squared.
Oh my God, Sedgwick, such enthusiasm and feeling. Nice, nice. Okay, so on the way up, we're slowing down. When it reaches its maximum height, what's the velocity? 0. Because we're going to stop to, oh, so at the top, it's going to end up at 0. Now, on the way down, it's going to start at
0.
and speed up. On the way down, Mary.
Yes.
Yes. On the way down, does your acceleration switch sign?
No.
You say that with no confidence whatsoever.
No. Wait. Yes. Yes, because velocity changes direction, so the slope of the velocity curve graph has to change to go back up.
No.
You were doing so well, Mary.
For about 2 seconds. You were doing so well.
Barry,
Gravity changes sign.
do you agree that the velocity time graph is going to start at 20?
Yes.
And what's the slope of that line going to be?
9.8 meters per second squared.
Positive or negative?
Negative.
Okay, yeah, right, okay. Otherwise known as the Olivia value, okay, right? So this is the Olivia slope from now on out, okay? Anytime we have gravity, it's the Olivia slope, okay? Which is going to be negative 9.80 meters per second squared. True? Where's the ball at this point?
Max.
Maximum height, because the velocity is
0.
0. Now, what's it going to do from here? It can do one of two things. It can either start back up like this, or it can keep going down like this.
Keep going down.
Because if it did this, which would be cool, okay? Yeah, if this was Timmy, so Timmy would reach the top of the peak after jumping off the trampoline, and then what would happen?
Zoom off.
Timmy would take off going up.
Then we're watching a horror movie.
No, not if it's Timmy. It's like,
Timmy.
it's Timmy. So, this is the Timmy curve, right? But that's not. So, we've got the Olivia curve, which has a uniform acceleration of negative 9.8 meters per second squared. So, Mary, back to your question. Back to your question. So, when this thing starts back down, what happens to that acceleration vector?
Stays the same.
Oh, it stays the same, because what's causing the acceleration?
Gravity.
This gravity switch signs on the way up.
Hopefully not.
Hopefully not. That would be weird. Okay? So, do you all agree that we're going to have the same acceleration the entire time?
Yes.
Okay, cool with this. Now, let's talk about this. Is the time to reach the maximum height going to be bigger or smaller than 1 second?
Bigger. Bigger.
Bigger.
You start out with $20 and you're losing
Yes.
$9.80.
Yeah,
every
you're
second.
starting with $20, right? Let's just round this to negative 10, okay? And if the Earth was a little bit more massive, that would be our gravitational acceleration. Oh, we're stuck at negative 9.8. If you're on the moon, it's like negative 1.5. If you go to Mars, it's like negative 3.6, okay? So we actually have a pretty decent gravitational field, which is cool because that allows us to have an atmosphere. If we didn't have a strong enough gravitational field, we wouldn't be here having this discussion because we wouldn't have an atmosphere. So, let's say this is negative 10. You show up, you have $20 at the store. You have to spend $10 per second. So at the end of 1 second, how much money do you have left?
$10.
$10. At the end of 2 seconds, you're broke. At the end of 3 seconds, you're in debt. At the end of 4 seconds, you're even
Bigger.
further into debt. Okay, welcome to American economics. No, it's true. Look at the amount of credit card debt that exists. People don't stop here. They keep going.
You get them,
Okay.
Dave Ramsey.
Huh?
You get them, Dave Ramsey.
Well, no, it's just true. I mean, it's just a reality. Oh, you must have the latest and greatest. No, you don't. Okay. All right. So let's make those all lines go away. Oh, one more. Okay. So roughly, roughly how long is this going to be? Roughly.
2 seconds.
About 2 seconds, right? This is going to take about 2 seconds. So where is the ball at that point? Maximum height, right? The Colorado point. This is as high as it's going to go. So, at that point, what does it start to do?
Go back down.
Go back down. Does your velocity change sign?
Yeah.
Oh, nice, nice. Okay, so if you were to find this area, what would it give you?
Displacement.
Displacement, which would also give you the maximum height. Ah, okay. All right, so we got all this. Now, what's your position time graph going to look like?
It's going to be a nice little roundable curve.
I like the sound effects.
It's going to be two Mick Jagger lips.
Two
Two
Mick
Mick
Jagger
Jagger
lips.
topic. Yeah.
That,
Face.
that, or the
I
inside?
want that top McJagger.
You like the top Mick Jagger lips?
Yeah, the bottom
Okay.
one would be cooler to see, but
Yeah. The bottom one would be cool, because what would happen? You'd throw it up in the air, and it would start off slow, then it would speed up as it went up, and then it would start back down really, really fast, and then it would slow down right before it get in your hand. Okay?
Helicopter could do that technically.
Yeah, but that isn't under the influence of gravity.
yeah, that's not Stoffela.
Yeah. Yeah. So we got the top curve. True? Nice. Okay, so let's talk about the time up. Go back to the 4 equations. How can we find the actual time to go up? What do you know? You know the acceleration, you know your
Initial velocity.
final velocity, you want to find time. So to get this point, you can go, oh, this is in my wheelhouse. V equals V naught plus AT. You know everything but
Time.
time. Now, this is where you pay attention to the units. I need time by itself, okay? Tori, how am I going to get time by itself?
Subtract V naught,
Yes, ma'am.
divide by accelerate.
Yes, ma'am. Pour it in the wheelhouse there. So, I'm going to take 0 minus 20 meters per second, and I'm going to do this wrong, and I'm going to divide by negative 9.8 meters per second squared. I'm going to flip out at this point. Why?
Here's not negative.
What's going to be the sign of your time? Yeah, you're going to have negative time. A little weird. But if you work this thing consistently, guess what? That's negative. Now I've got 2 negative numbers. I'm going to get positive time. Here's what we need. So somebody take 20 and divide it by negative 9.8.
2.04 seconds.
2.04?
Yeah.
Now, that matches with what we said.
Yeah.
Okay? We said it's going to be around 2 seconds because you showed up with 20 bucks. It took you about 2 seconds to go broke. Okay? I mean, maybe unless you go to the casino after you let it all ride on,
One
No.
bet.
yeah, on one bet. Here you go.
Will the time down be the exact same as the time up?
Yes. Now, there's a huge caveat to that. So, if you want to find the time down, here's the deal. If it returns back to that same point, okay, and that's a huge if. If it returns back to that same point, the flight is symmetrical. So if it took 2.04 seconds to go up, it's going to take you another 2.04 seconds to get back to that same point. So it's going to go from 20 to 0, and then it's going to land at
Negative 20.
negative 20. If it's symmetrical. Now, if I do this, and it falls farther, then it's not symmetrical. But if it returns back to that same point, it's symmetrical. So this point out here is going to be total time, then is going to be another 2.04. So that's going to be 4.08, and that's going to be negative 20 meters per second. Now, let's talk maximum height. If there's like 3 different ways you can find the maximum height. I don't care how you do it. I do not care. But there's 3 different ways you can do it. One of them is that you go to this velocity time graph and you go, oh, wow, that looks like a triangle. I know how to find the area of a triangle. Do you know the height?
Yes.
20 meters per second. Do you know the base?
Yes.
Yes.
Yes. And you know the area of a triangle is 1/2 base times height. But what's the disadvantage of this?
Using your time
You're
value.
using your time. If your time up is wrong, this is going to be wrong. But if you're solid on the time, and you want to go with this, hey, find the area of this triangle. It's cool. You've got it done. So if you want to do this, you could just go, oh, area is 1/2 base times height. Basically, you're going to take half of 20, which is 10 times 2.04. You're going to get 20.4 meters. Okay? So, if you like triangles and finding areas of triangles, this is in your wheelhouse. Okay? All day long. You can do this. And it works. But you go, oh, Mr. Urkamp, I like formulas. Okay. you've also got this. You know the final velocity
Yeah.
on the way up. You know the initial velocity.
Yeah.
Yep. And you know your time. So here's the cool thing about this. This is basically the exact same thing as area equals 1/2 base times height, because this is like this triangle here. So here's your base, that's your time. Here's your height, which is your initial velocity. You're taking half of it, which is the exact same thing you're doing here mathematically. So if you like formulas, do this. If you like triangles, do this. But to both of those, what's the downfall?
You use
Using your
time.
You're using time.
We need that.
So is there a way to find the maximum height without using time?
That equation.
Oh, that equation. That's in your wheelhouse. So you got v squared equals v naught squared plus
280.
2AD. You know everything but what?
D.
D.
Your distance. So Ethan, get D by itself.
Subtract V naught,
Then what?
divide by 2A.
Divide by 2A. Life's good. Now, should this number work out to be a positive or negative number on the way up? Should be positive, okay? Should be a positive value. Now again, this is paying attention to the details. On the way up, your final velocity is going to be 0. So I got 0 squared minus 20 meters per second squared divided by 2 times. So notice this is not negative 20 squared, okay? That squared value is outside of that minus sign, okay? So, am I going to get a positive displacement?
Yes.
Yeah, I am. And you should get 20.4 meters. So, you can't have one set of equations producing a distance of 20.4 meters and another set of equations producing a maximum height of like 25 meters. You have, they both, no matter how you work the problem, you have to end up with the same maximum height. Cool with this? Nice. Now, we got one thing left to do. Actually, a couple things left. So, we got this, 2.04, time down, 2.04, maximum height, 20.4. So, the velocity and height at 1 second. There is only one way, and only one way to work these two problems. You don't have another option. What's the only way that you can figure the velocity at 1 second?
V naught is AT.
V equals V naught plus AT. That is the only way to work this. Now, here's the beauty of this. If you think through with the money analogy, at the end of 1 second, how much money have you spent?
9.8.
Well, about 10, but realistically, actually you would have spent
$9.8.
$9.80. You started with 20 bones, right? So at the end of 1 second, how much money do you have left?
11 and 20.
Yeah, $11.20. Okay? If you want to go with the money analogy. So here's the deal. So the only way that you can do this, and again, think this through. All we're saying on these velocities is that it's a slope-intercept form. That's all we're saying. Your initial velocity is 20 meters per second. That's your y-intercept. You're going to, at the end of 1 second, you're going to go over 1 and down 9.8. You're just trying to figure out what the velocity is at that point. Now, before you do any calculations, listen to me. Is your velocity at 1 second going to be a positive or negative number? Why? Why, McGriddle?
It's like still slowing down. It's not like completely changed direction yet.
How do you know yet? How do you know?
Because it's still under the, was it the 2.04 seconds?
Yeah, because 2.04 seconds is when it's at its maximum height, right? So you know this thing is still on its way up, so you know your velocity has to be a positive number. Now at 3 seconds, your velocity is going to be a, because now you started on the way down. Okay? So before you crunch any numbers, look at the entirety of the problem and go, okay, hey, what's happening here? So, basically, to get these velocities, let me kind of, so the only thing you're going to change on these problems to get that velocity, basically, you're going to take 20 meters per second plus negative 9.8 meters per second squared times whatever value of time that you have. Plug in 1 second, plug in 3 seconds, plug in whatever. Now, if you plug in 4.08 seconds, if you plug in 4.08 seconds, what are you going to get for that velocity?
Velocity of impact.
No, you won't get 0,
The velocity of impact.
You're gonna get the velocity of impact.
which is going to be what? No, it's not going to be 0.
Negative,
Maybe.
Negative what? Jones, what?
negative 20.
Negative 20, right? Oh! Yeah, because if you plug in the entire flight time, you're going to get negative 20. If you plug in 2.04 seconds, you're going to get a velocity of 0. Oh, that's good. Like that. Okay, now, so if you plug in 1 second, what do you get for your velocity? Basically, take 20 and subtract 9.8. What do you get? 10.2 or 11.2?
11.2.
10.2.
I got 10. It's 10.2.
It's 10.2, right? Not to be confused with 10.2. So, 10.2 meters per second. Now, here's what I want you to understand. And this is where this thing goes big picture. If you were to draw your position time graph, okay? And if you were to come out here at 1 second and draw that tangent line, what would the slope of the tangent line be at exactly 1 second?
Negative 9.8 meters per second.
10.2 meters per second, because that's how fast it's going at the end of 1 second.
Yeah.
Right? So this slope of this tangent line is 10.2 meters per second. If you go out here to 2.04 seconds and draw the tangent line, it's going to be 0, because that's when your velocity is 0, and that's when you're at its maximum height. Now, if you go out here to 3 seconds, right away, what do you know the sign of that tangent line has to be?
Negative.
Negative value, because now you've started on the way down. So if you go to this, oop, one more. So the only thing that changes is that now I'm going to put in 3 seconds. So somebody take 20 plus negative 9.8 times 3.
Negative 9.4.
What'd you get?
Negative 9.40.
Negative 9.4? Does that make sense? Why that's negative?
Yeah.
Yeah, because now we're on the way down, and it's negative 9.4. Now, to get the height, 1 second and 3 seconds, there is only one way to do this. There is no other option. The only way that you can do these is if you use that distance equals 1/2 AT squared plus V naught time. That is the only way to work this problem. There is no other alternative. But all this is, if you think about it, this is just a function equation that generates different values of height for different values of time. Because make sure, when you do this, make sure that you're using negative 9.8 meters per second squared. Do not make this positive, or otherwise you're going to be adding 2 positive numbers together, and you're going to get a height that's way, way, way too big. So, then you got that time squared, then plus, what's your V naught value? 20 meters per second, 20 meters per second times whatever value of time that you get. If you do this, what can your answer never be bigger than? 20.4. Why?
Because that's your maximum.
That's your maximum height. So if you do this and you plug in 2.04 seconds for time, what should you get?
20.4.
You're going to get 20.4 meters. So to do this, so let's do this. If you plug in 1 second, that one's easy, right? So you got 1 squared times negative 9.8 times a half, which gives you negative 4.9. And then you've got basically negative 4.9 plus 20 is going to get you like 15.1. So at the end of 1 second is 15.1 meters tall. The only thing that changes is that when you get to 3 seconds, you plug in 3 seconds here. That's the only thing that changes. It's just a function equation. Okay? Got it? Good? Okay. Stop that. Let me get you started on this assignment. 1 through 4 has nothing to do with gravity. So 1 through 4 is old school like you did yesterday. It isn't until number 5 when you start using gravitational acceleration. So let me paint the picture on number 5. On number 5, you're standing on top of a bridge and you're going to drop a rock. So to make sure everybody's cool, we're going to make the bridge be the reference point at 0.0 meters. All of your displacements and velocities going down are going to be negative numbers. So when I say how far has it fallen at the end of 1 meter, this is going to be a negative value. 2 seconds, negative value. On all of these, the beauty of it is V naught is going to be 0. So basically, I want to know how far it's fallen at the end of each interval, and I want to know how fast it's going at the end of each interval. All of your displacements and all of your velocities on number 5 should be negative, because we're defining down as being negative, and we're starting at 0. When you get to question number 14, okay, when you get to question number 14, you're shooting a mortar straight up in the air, initial velocity 50 meters per second. It explodes 5 seconds later. So how high is the mortar at this point? Do not use on anything relating to number 14 that equation. And here's the reason why. Because you don't know if it's on the way up or if it's on the way down. Okay? Because you don't know when you just know it's exploding at 5 seconds. You have a specific time. So in number 14, do not in any way, shape, or form use that equation. Because you don't know enough information to use that equation because you don't know which route to pick. When you get to number 15, you've got 3 people standing on a bridge. One person throws it up in the air, whoop. Another person just drops it, and then another person throws it down. But here's the whole key to number 15. As soon as it leaves your hand, the Jedi Stofel thing, no matter what, if I throw it up, throw it down, or just drop it, as soon as it leaves my hand, what's the only force acting on that ball?
Gravitational.
And what's the acceleration due to gravity, Olivia?
Negative 9.8 meters per second squared.
Beautiful. Okay? So guess what? Even if you throw it up, throw it down, drop it, it's going to have the exact same acceleration. Okay? Keep that in mind. Now, here's the other thing. Look at every problem on here. I have never given you the mass of the object. Do you know why?
Because it's constant.
It doesn't matter. The mass, you can't look at your first 4 equations. Can you plug mass into those equations at all?
No.
No.
So if I drop Hank or if I drop Gary the golf ball from the same height, mathematically they are treated the exact same. You cannot plug mass into these equations if you try. Do not forget, where do I want the answers? On the left. I want the work on the right. Keep it all very organized. Go fly, be free, have a good weekend.
For number 15, do you want the graph on a piece of graph paper?
You can do it on that